Hello there, people. I have been meaning to do this video for a while. Yeah, I've been really meaning to do this video for a while. And the point of this video is to take any developer, obviously Python developer, but if you're not a Python developer, you're going to understand some of the stuff I'm talking about. But the point is to take you from zero to hero when it comes to all things around AI application development that we're seeing today. I'll be talking about some tools. I'll be talking about a database, a vector database, MongoDB. I'll be talking about embedding models and re-rankers from Voyage AI. And I'll be talking about OpenAI. I think everyone knows OpenAI, but what I'll be talking about mostly is how we use the LLM. And also, I'll be going into the OpenAI Python SDK, agent SDK framework. So we're going to be looking at how we can make agents using OpenAI's framework. So I really don't know how long this video is going to be, but here's my promise. By the end of this video, you'll be able to understand a lot of the things you hear in the space of RAG, which is Retrieval-Augmented Generation, and AI agents in single agent and multi-agent. So that's my aim, to just get you from, I don't know what's going on in this space, to, okay, I understand and I can run some code and I can speak about it. So this material is split up into 5 sections. So let's go over what we're going to expect. I'll put some timestamps in the video so you can skip to any parts that you see is more relevant to you. So in part 1, we're just going to talk about the use case within this notebook in particular. And this notebook is available online. The link to the GitHub repository for this notebook is in the description of this video. But in part 1, we're going to be talking about the use case of this notebook. We'll also be talking about some of the tools that we're using. We're going to be looking at getting data from Hugging Face to actually use as a knowledge base for our agent and also the knowledge source for a RAG pipeline. And we're also going to be looking at the embedding process. How do we generate this data object that is essentially a numerical representation of files and images that is able to be used within semantic search and vector search, right? How do we actually get those? How do we create a function that can pass data into an embedding model and we get the embedding, right? Then in part 2, we're going to be looking at how we can build a RAG system, a RAG pipeline. In part 3, we're going to take things a bit further and go into the world of AI agents, particularly looking at things from the OpenAI perspective, how we build agents using the design paradigms and nomenclature of OpenAI. Then in part 4, we're going to be building an AI agent that has some form of memory, persistent memory. The interaction will be saved in MongoDB, which will be our database of choice here. And we'll be able to go back to previous interaction. Then in part 5, we're going to take the memory understanding and actually build upon it and go into other types of memory like session-based memory and use the OpenAI agent SDK library to actually make that happen. So, like I said, I don't know how long this video is going to be. I'm just going to record and make sure I provide value to you guys. And if there's any stuff you guys would like to see me do in the future or create notebooks for, let me know. Obviously within the realm of generative AI and AI agents. On that note, let's get started with part 1. So the use case of this notebook is a virtual primary care assistant. What does that mean? If you're building a healthcare chatbot, then this notebook is for you. Or if you're building any sort of chatbots, the paradigms and the steps we take will be relevant and transferable to your use case. But the end goal of this use case is to have a system, a chatbot system that we can interact with, ask questions about medication, and it will give us some recommendation. But also, it can actually give us information on past conversations or maybe some guidance on certain diseases in some health conditions as well. It's a healthcare agent that could be an assistant to a doctor or a nurse per se. So that's what we're trying to build. This agent needs its knowledge base, right? Which is the first part of this. We need some data. So let's go into the data aspect. Before we actually get into that, I actually have a visualization of what we're building. Over here, we have our data source, right? So we have a bunch of data. We're using a healthcare conversation data set and a drug reviews data set. We're going to be getting this from Hugging Face in the right over here. So the data set is from Hugging Face. You can get it. I'll put a link in the description as well. And you can get this data set here. And this is just a conversation between a patient and what looks like a chatbot, right? So this is some previous conversation we can give to our agent and use as a knowledge source. The second data set is actually a data set of various different drugs, the condition that they basically treat against, and some reviews from some real life users that have used the drugs and they've given their reviews on this as well. This will help the AI agent that we're building actually understand some drugs and maybe even some conditions and the drugs that corresponds to the conditions, but also some reviews that people have had, maybe side effects or if it worked or didn't work. So there is a lot going on here. We have two data sets, and over here we have the repository for this notebook that we're going through. So you can access this publicly, and I'll put the link below. So if you go back to the code, so we have our data source, and we're actually going to do a couple things. We're going to take our data source and generate embeddings, which are this numerical representation of data objects that we can use to conduct semantic similarity and vector search operation. Essentially, the key takeaway here is by generating embeddings, we're going to create another component of data that allows us to search by meaning. Traditionally, we've done things like text search, we've done things like geospatial search, where you're searching by location. We have text search, where you're searching by text query. With vector search, you use embeddings to search by meanings because these embedding models capture the meanings and context, the semantics from whatever data objects you're passing into it. We'll talk about this later again. So once we have all of this data, both the text conversation and the reviews, and we have the numerical representation, the embedding, we're going to ingest them into MongoDB Atlas. That's going to act as our operational database, and our vector database is going to act as our AI database, essentially. And then we have a bunch of ways we can retrieve data from MongoDB. We have text search, vector search, and hybrid search, which is a combination of these two searches, right? So you'd have to choose one. You can use both text and vector search and then balance them accordingly. So this notebook goes into a lot of detail. So again, you can skip to whichever part that you feel is relevant to you. But one thing we're going to do is with this, our search methods, we're going to do two things. One, we're just going to create a simple RAG pipeline, right? And this is RAG is a keyword, and this notebook will show you how to implement that, right? We're going to build a full RAG pipeline. But at the same time, we actually going to use the search method and give it to our AI agent as tools. So our agents will have different ways to search for data based on an input query and then respond to a user with some medical guidance and all the good stuff that a healthcare chatbot should be able to do. So that is what we're working towards. It's going to be fun. So that's part one, the overview of the whole thing. Now let's actually go into some of the libraries we're going to be using. So in part one, we're going to actually get our data. We're going to generate our embedding, and then we're going to put in a MongoDB database. I have the MongoDB database over here. Again, MongoDB, you can create a free account with MongoDB, and then you can actually go through this notebook. There's some caveat, but I've kept some notes, but you can actually create a free account and go with this notebook, and I'll walk you through everything, including what the database looks like and the collection within the data within the collection as well. So first thing we're going to do is some libraries we're going to be using. We're going to be using PyMongo, which is it's basically a Python driver for connecting to MongoDB databases or MongoDB clusters. We're going to be using Voyage AI. Now, Voyage AI is a company that creates state-of-the-art embedding models and re-rankers. So embedding models is what we use to create the vector embeddings that we need for semantic search. And we're going to be using the Python client for this. And Panda is a very general data science library, and it's used for modifying data structures using a Python language, right? So it's very effective for visualizing maybe some structured data like tables, and we can visualize them as data frames and all the good stuff. So datasets is a library from Hugging Face. We're going to be using this to load the data from Hugging Face like I showed over here. So we're going to use this to load the data. And then we use matplotlib for some visualization as well. So it's going to be fun. I'm going to actually run this live as well. I'm sure there will be some errors. Let me clear the outputs actually. Let's run this live. So the first one we're going to do is we're going to pip install. I've already created an environment here. I use Conda to create a virtual environment. So all the libraries and all the package I'm installing are actually isolated within a certain segment that is not going to pollute my entire local machine directory. So we're going to pip install PyMongo, Voyage AI, Pandas, datasets, and matplotlib. Let's run that. Okay, that's run successfully. There's a bit of an error here, which is fine. Things will still be fine. Let's go. So we're going to have a bunch of API keys, and we need to put them in our environment variable. So that's what this function does. I just created a generic function that's called set env securely, set environment variable securely, and it passes in the variable name and then the actual variable, the actual value itself. So that's what we're going to do. So this is just generic function that we're just going to have run and use in various places of the code. Okay, so for step 2, we're actually going to do a couple of things. We're going to ingest our data. So I've kept a link to where I got the data from, but I've shown you already. So let's ingest our data. So the first thing we're going to do is import the pandas library, as we've used the namespace PD for it. And we're going to, from the datasets library, we're going to import the load dataset method. Then let's run this. Okay, so we have we've just run this cell and we have what we need. So in the next cell, what we're doing is we're importing the data set into our environment. So we have the healthcare conversation data set, which is right over here, which has a bunch of queries from users and then an output from what looks like a chatbot, right? Chat doctor is what it's called. There's information into over here. There's more information needed, but this is a public data set. So if we go back, so we're going to actually import this, put this into an environment. We're going to make it streaming and we're just going to get the train partition of this data set. And once we do this, we're going to assign it to this variable, healthcare conversation data set, which will give us all the data points within the train. But it's streaming because I don't want I set streaming to true because I don't want the full data set. I just want to actually take 1,000 data points from this because it will just save a lot of time. But if you want, you can get the full 100,000 medical conversation. So I guess you have a lot of knowledge data points. So we're going to run this. And this is now going over to Hugging Face and now getting this particular data set. And we're actually just going to take 1,000. That's why we have streaming set to true. Okay, so we do the same for the second data set, which is the drug reviews data set. So let's run this. And we're assigning to this drug review data set variable. So we have 2 data sets. So right here, we're going to create data frames for the healthcare conversation data set and the drug reviews data set. And this will allow us to easily modify this the data set and also visualize it as well. Okay, so we have the data frames created. Next, we actually have this. So there's this step that I'm doing is where I'm actually from the healthcare conversation data set. And this is why we use pandas, because it's very easy to modify data. We can just drop this column instruction. I actually don't need it. So if we go back to this data set, I have this, there is this data point here called instruction. I don't need it for this particular use case. So we're just gonna drop that. And that's the point of using pandas, is that you could just easily modify data very, very intuitively. So we're just gonna use the drop method and specify the particular column we wanna drop. And also in the drug reviews data set, we're going to do the same thing and drop some other data points that I don't need. Okay, so that's done. Now we can actually visualize what the data looks like. So now the healthcare data set looks very simple. We just have the input, which is coming from the patient, and then we have the output, which is coming from the healthcare chatbot. Very simple. Then the drug reviews data set is also simple, where we have the drug name, the condition, and we have the review, and we have the rating of the actual drug. In the next step, in step 3, what we're doing is we're going to generate embedding. And I'm using the embedding model Voyage Free Large. I've kept a link here for you to access more information on the model. Very quickly, Voyage Free Large at the time of the recording is one of the best embedding model, hands down, in terms of within the space now. with Voyage AI, you could get around 200 million tokens for free, which is about, I don't know, maybe 5 to 10 Harry Potter books. I'm not sure. But you can basically build out your POCs with this amount of tokens. So you can just go and get your Voyage AI API key and keep it within your environment. So I'm just going to quickly go grab mine. Okay. So we have our Voyage AI API key, which is good. Now we actually have the Voyage AI Python client, which we pipped installed earlier on. So we have a reference to the client. This variable actually references the client directly, and this will allow us to access all the methods we need. So we create this function get embedding. It's very straightforward. What this function would do is we're going to take in a text, right? We're going to take in like a text data, and we have a task prefix. This could either be document or query. I'll explain that in a second. So we're going to take in a text, and this would be any sort of like textual data. And what I'm doing there is just I'm removing all the spaces within the actual text at the end or at the start. Then what I'm doing now is I'm passing the text into the embed function or within the Voyage AI clients that we initialized earlier. And I'm specifying that I want to use the Voyage free large model, and the input type is a task prefix. Now I said I was going to explain it. So the task prefix at this moment is it can either be document or it could be query. Right now it's document because what we're doing is we're going to embed a bunch of documents. And now when we actually get a user query that comes in through our chatbot, we can pass in the argument here to be query. So we embed the query with a specific instruction on how to embed the document and how to embed queries. So that's why we're actually specifying the input type here. Then the result of this is going to return to us an embedding. We're going to see what that looks like in a second. And that's what this function does. We're going to use this function a lot throughout this notebook. So get embedding is a very simple function that takes in a text and outputs a numerical representation of the text that we've passed in. So let's just run the cell. Let's now create a function that allows us to generate embeddings for the healthcare dataset. What this function actually does is it takes in a row essentially and creates conversation text. Remember, a row from the healthcare dataset contains the input from the patient and the output from the chatbot, right? The healthcare chatbot. So I just do a bunch of concatenation, just saying this is the input from the patient. We have from the row, we extract the input, and this is the response from a medical practitioner. And then we have the output. And then we call within this function, the function we created earlier, which is the get embedding function that will convert this text, conversation text, into a numerical representation. Okay, so I'm using this library TQDM to actually see the progress as we're going along. So let's actually see within the actual healthcare dataset, we're going to create a new column called embedding. This will hold that numerical representation. And we're actually going to use the function from the previous cell, generate embedding for healthcare dataset on each of the rows within this actual dataset. And it will put the result of this function into the column embedding. So we'll see that in action. And we can see the progress bar here. This might take a while, but that's fine. And we'll come back when this is done. All right, so that's now done. Now let's do the same thing. We can actually view what the data set looks like now. So here we can see the input from the patient, the output from the chatbot. Now we can see this embedding, right? So like I told you, an embedding is a numerical representation of any data object that was passed into an embedded model. And this is just an array of some float 32 values. And here we can, remember we concatenated a string that had this, the input and the output, and now we have this embedding that is a combination of the input and the output. The point is, when the user passes in a query, or when we have a query, I can then actually use that function get embedding to convert that query into another numerical representation. And in a high dimensional space, we can see we could conduct a vector search operation that uses a distance function to see how closely two vectors are in latent space. And what that means is the closer they are, the more semantically similar the context that has been captured within this numerical representation are, essentially. So that's the aim here. To essentially, we have all of this input and output conversations, and we can have an input query. Then when we have the input query, we can get the the right conversation points that are actually relevant to the input query that we're getting from our user. So we're going to do the exact same thing for the drug data set. So we're going to generate the embedding just from the review data point. So in the previous data set, we generated the embedding from a concatenation of the input and the output data point. But now I just want to use the review to generate the embedding for each of the data point within the drug review data set. So again, we'll wait for this to get done and we'll come back. So that's done. Now we can see what it actually looks like. So now we have a drug name, we have the condition that the drug treats, we have a review from a patient that's utilized the drug, and then we have a rating. And now we also have this embedding that's the numerical representation of this data object that is the review. Okay, so for step 4 of part 1, what we're going to do is we're actually going to go get our MongoDB connection string. And I've kept some links here to help you create a pre-MongoDB account and follow the instructions here to actually deploy your cluster. And then you can follow some instructions to get your connection string, and it should all be straightforward. Okay, so let's get our MongoDB connection string or MongoDB URI. All right, so once you actually pass in your connection string into your environment variable, what you're going to do is you're going to import PyMongo. Remember, we imported this earlier, and we're going to create a function that just does something very simple. It basically just returns a MongoDB client. And what the MongoDB client does is it gives us access to our cluster, to our database, and to our collections. So we can actually start to do some operation using the PyMongo driver, Python driver for MongoDB to actually manipulate and ingest data into our MongoDB database. So here you can see that we have the get Mongo client. It takes in the URI. It's a function that takes in the MongoDB connection string. And from that connection string, we can actually make a connection to our cluster. This line here just validates that we have a connection by pinging the cluster. And if we get a response, then we're ready to utilize the actual client. Okay, we're going to run this cell. And here we're going to see there's also an error check here just to make sure we have the Mongo URI in our environment variable. Okay, let's actually use the function we just created. We'll create a variable called Mongo client and assign that to the result of the get Mongo client function. We're going to pass in the Mongo URI. Remember, the Mongo URI comes from the environment variable over here that we just set earlier on. And that's it. So when we run this cell, we're going to get our MongoDB client. Next thing in that we actually do here is we're going to create a database name. So the database name is Virtual Primary Care Assistant. You can call this whatever you want, but I'm calling it Virtual Primary Care Assistant. Then remember, we have 2 data sets, right? We have that drug review data set and we have the conversation data set. So we're going to put this in 2 separate collections within our MongoDB database. And that's what this line is just basically creating a name for them. So we're going to actually get the exact database from the cluster we have here, and we're going to assign that to this DB variable. We created an array for that we placed in the name for the collection. So what we're going to do is we're going to iterate through this array and create a collection within our database if it doesn't already exist. So we have this .list collection names, which actually looks at our database, and this is an array of the collections within our database. And if the collection name is not in the database, we're going to create a collection with that collection name. We're going to use the create collection method on the database client, and we're going to be able to use that to create a collection using this collection name. Next is and we're going to catch, we have an exception that can catch it's going to be a try and catch, and we can catch any errors. Okay, we also, if the collection is not in the name, we create it, but if it is in there, we actually can say that this exists. So once we're done and this runs successfully, what we can actually do is assign a reference to the collection to specific variables within our development environment. For example, for the drug review collection, we want to actually have a reference to that collection. We have this database object that corresponds to the database in MongoDB. And then we have the collection name, and that will give us a an object that references the collection within our database. So we're going to run the cell, and we can see that it's running and there will be some output. So we have our connection to MongoDB that was successful. We have the collection drug reviews was created successfully, and we have the collection conversations were created successfully. And we can see what that looks like in MongoDB Atlas. So we're just going to refresh this very quickly. So I'm connecting to my cluster here, which the database was created in cluster 4. And we go into the database. So you can see here, I'm just going to zoom in a little bit here. We can see here we have the virtual primary care assistant, which is the database we created. And we have these 2 collections, which is the conversation and the drug reviews. If we go into the conversation, it's empty. This collection has no data. We go into the drug reviews, it's empty. This collection has no data. Let's rectify that. Before we actually ingest data into our collection, we have to create what is called an index, right? We have to create 2 types of index, a vector search index, and we have to create a search index as well. I've explained why we need a vector search index and a search index. So generally an index, you can see it as like a data structure that actually allows for the efficient retrieval of some data within your actual database, within your records. And the reason why you would have an index, and it makes more sense when I explain it using a book. Imagine you have like a textbook and you go into like the glossary page of the textbook. That allows you to quickly maybe look at a particular topic, and then it tells you the pages where the more detail is located within the textbook. That's what an index is. It's a data structure that allows us to locate some data within our records or collection very quickly and efficiently. If we didn't have it, what would happen is we'd have to scan through the entire records within our data set or within our collection to actually retrieve the data that we actually require or the number of documents we require. So we have a vector search index, or we have a search index. You can read this and see the vector search index we're using. We use for particularly in the MongoDB database, we use the hierarchical and navigable small world, HNSW. And I think I linked to the paper here. So this paper talks about what the algorithm is. There's also more about on MongoDB as to how you can use how this vector search index is implemented and used in MongoDB. Okay, so now we can actually look at how we're creating our index, right? So we have a function called setup vector search index. And the reason why we have this as a function is because we're going to do this twice. So I just kept it within a function. This function is going to take in a collection. It's going to take in an index definition. We're going to see what that is. And it's going to take in a name for the index and any fields that we're going to filter on. I'll explain what that is as well. If we have a filter field, what we're actually doing here is a filter field is basically a way to shorten or reduce the search scope of your vector operation. So imagine in this use case, I'm actually having a filter field on the condition attribute of our document. And that means if I have a condition like cough, if I want to do my vector search operation, I can actually just add the filter to actually do the vector search operation on documents that have where the condition of the disease I'm trying to look for is cough. We're going to see this in this notebook, and it's called pre-filtering, and it gives you a better retrieval latency, a reduced retrieval latency, because you don't have to traverse through as much nodes doing your vector search operation. So that's what this does. It's just basically creating a object. So you specify the type, which will be filtered, and the path will be the location of the attribute that you want to create a filter on. But then we actually go into the actual index creation. This is setting up the vector search index. We create the vector search index here. We print the index definition. And over here, what we're actually doing right here is where we are creating a search index model. Specifically, we're going to pass in the index definition, which is obviously this data object. We're going to pass in the index name. And just to clarify, we already have this index definition getting passed in. And what we're doing in this line is we're just adding this additional object to this existing index definition. Then in the search index model class, or in the search index class that we get from the PyMongo operation module, what we're able to do is actually create a model of our index, which will have the index definition, We have the name and the type of the index we're creating. And then on the collection, we can call the create search index method that takes in the model of the index we want to create. And we run this, and then we're able to create our index. So that function is all good for us to use. And now this is what an index definition looks like. So we have the type, which is a vector. We have the path of where the embedding is located within the document, which is called embedding. Then we have the number of dimensions. I should have mentioned this earlier, but we have the number of dimension of the embedding. Number of dimension of an embedding is basically the number of values within the list or the array within the embedding itself. So if we go back up here, over here, we saw we had like a list of several different numbers. The numbers, the amount of numbers inside of this list is going to be 1024 because that's what the Voyage Free Large outputs by default when you actually utilize Voyage Free Large for embedding generation. Now you can change the dimension of the embedding. You have to look at the documentation to see what other dimensions you can have your embedding get outputted with. The reason why you might want to change the dimension of embedding maybe to one that is lower is just to maybe save on storage cost. So if you're saving an embedding with lower dimension size, maybe 256, obviously you're using less storage space, you're using less disk and RAM space. So that will overall save on your storage cost. So that's why some people might actually look to use lower dimension sized embedding. Okay, if we go back to the index creation, we've just explained the number of dimension. You have to make sure this matches what the output of the dimension of your embedding is. Then the similarity. Now, remember I said in a high dimensional space, we can work out how similar two vectors are to each other by measuring the distance between them. And we do that using different distance measures. So one is cosine, which is overhead. Another one is dot product. And the other one is Euclidean. Can I spell that? Yes, I can, with a little bit of help. So you have to choose one of this. Just rule of thumb, most folks just go with cosine, sometimes dot product as well. It's beyond the scope of this notebook, of this video, to explain in detail what each of these distance measures are. But you can go and look online to see what they are. They're basically mathematical operations to determine the distance between two vectors. Here we can run this code and we assign this index definition to this variable. And we have this vector index definition float 32 ANN. It's an extensive name, but it's basically float vector index definition is what it is. Float 32 is the precision data type of the embedding that was generated. And then we have approximate, ANN stands for approximate nearest neighbor. So here we actually have the name for the index. So this is the index name for the actual index. So this here, it's kind of confusing, but this here is the index definition, the JSON object itself, the data structure itself. But over here, we have like our index name. There's a bunch of narrative here that I've just mentioned in terms of the point of having pre-filter fields in your vector index. Here, we're going to do a couple things. In this cell, we're actually going to set up our vector search index, right? Very simple. I'm just calling the function vector set up vector search index. I'm actually creating some filter fields, right? Remember we spoke about the filter fields earlier. For the drug review data set, I'm creating a filter fields on review and condition. For the actual conversation data set, I'm creating a filter field on the input and output. So now I'm going to I'm using the function setup vector index vector search index that we created earlier on. And I'm just going to run this cell, and this is going to set up the index for us. And that's it. We're going to create a search index as well. So the search index is a bit more straightforward. We have an index definition that contains a name, type, and definition. The definition will be passed in, the full definition will be passed into the set text search index class. And we have the index name. You have to give the index name. And here it's very simple. We have the model of our index, and then we use the collection.create search index, which is the same thing we did before. But now we're passing in a search index model, not a vector search index model. In this case, it's a search index model, and we're able to pick up what type of index it is because we specified a type search over here. And we could run this cell, and we're going to create the index definition that will pass into the function. Here, we're just going to specify that the mappings, we don't want it to be, the dynamic attribute is set to false because we don't want it to dynamically create index on any new attributes that come in. We only want index created on the drug name, the condition, and the review attributes. Next, we create this text search definition, quite simple, and then we pass the actual definition into the function, right? We set up the text search index for the drug review collection. We set up the text search index for the healthcare conversation collection, and that's done. In step 6, we're going to move into the data ingestion. So this is kind of like important. We actually have to take the data. Remember, we have to put the data into the database, right? So here we have the healthcare conversation data set, and we're also going to ingest the drug review collection. So here we have the healthcare conversation data set. We're going to convert it into dictionaries before we add the data frames. And each data frame, we add the rows. Now we're going to convert each row into a dictionary. So we have the toDict method in the pandas data frame object for the healthcare conversation data set. And we do the same for the drug review data frame as well. And once we've done that, essentially what we have is this data object that we can just use and insert into our collection. So we have our healthcare conversation collection that we initialized earlier, and we can call the insert many method and in bulk do a batch insertion of all the data set that we've just prepared. And this is all we need for the data ingestion. There's no massive data transformation that we're doing here because MongoDB under the hood, the data model within MongoDB, the data type and how data is stored is using the BSON data format, which is basically binary JSON, is an optimized form of JSON. And that's why you can actually have this JSON-like data structures are easily ingested into MongoDB without any transformation or serialization. So we're ingesting the data, and once this is done, we're going to have a look at it in MongoDB Atlas. Okay, so the ingestion process is done and we have the output here. Let's go into MongoDB Atlas and see what that looks like. So we can actually just refresh our collection. I'm just going to hit the refresh button over here. Okay, that's been refreshed. And we can see we have 1,000 documents in the conversation collection. We have 1,000 documents in the drug reviews collection. And we can look at what that looks like. Okay, so in the conversation, remember we had this input, we have the output, and you can see we have this additional data, we have this additional attribute in our document called embedding, which is 1024, and it just has floating point numbers in a list, in an array. So that is, and we just have about 1,000 data point. Remember, we only want 1,000 data point, but the data set goes up to, I think, 100,000 data points. So we have several data points, and you can take some time to look at what this looks like. And we have the same thing for the drug reviews as well, where we have this drug review collection in our virtual primary care assistant database, and we have a drug name, the condition it treats, and the review of its utilization along with the ratings. And we have an embedding that is generated from the review. And what you have here is your metadata sitting alongside your embedding. Essentially, you have one database to handle all the data you need for your AI workload. Let's have a look at the indexes we create, what that actually looks like. So to have a look at that, you can go into this index. You go into where we want the search and vector search indexes. And we go into here, let it load. And here we can see the indexes we created within the drug review collection inside of the virtual primary care database. Here we can see we have the text search index, and we have the vector index float 32 ANN. We can see what that looks like. And that has the vector path is embedding, the number of dimension is 1024, the similarity method is cosine, and the filter fields are on the review and condition paths. And we can see what that looks like in JSON. So that's loading, and we can see that this is what it looks like in JSON. This is that data structure of the index. So we have the number of dimension and we have the filters. And this allows us to conduct efficient vector search operation within the database. Okay, we can go back to the index overview. We can take another step back and which actually go back into the data explorer and go back into our database. We go back into our cluster and we can see that we have our collections here. Okay, let's go back into the notebook. And we can actually, in step 7, what we can actually start doing is looking at how we can build out retrieval methods using MongoDB. More specifically, we're going to be using 3 operators to essentially build out retrieval method. And we're going to be using the search operator, which allows us to do lexical search. This is MongoDB Atlas search. We're going to be using the vector search, which allows us to use MongoDB Atlas vector search to actually conduct search by meaning. This is search by text, search by meaning, and we have the rank fusion operator to combine both of this in one unified search. But we're going to see all 3 because in your retrieval pipeline, you might need to maybe use search, or you might need to use only vector search, or you might need to use both. You have to actually evaluate the certain metrics within your RAG pipeline or your retrieval pipeline to actually determine if you want to be able to maybe look at other search mechanisms, retrieval mechanisms to optimize maybe the recall or precision metrics that you've evaluated your RAG pipeline on, or your retrieval mechanisms on. A quick note: rank fusion is only available at the moment of this recording on MongoDB 8.1. So we're going to create a function called text search with MongoDB, very descriptive. It's going to take in the query text and it's going to take in the collection where I want to conduct the search against. And we have a top n, the number of results we want to return, and the path that we want to conduct the search against, right? So reviews has a bunch of text search, has a bunch of text data. We want to actually conduct the query text and see if the query text is within the text data within the review attribute. That's what we're essentially doing with text search. So what we're doing first is we have the search operator, like I mentioned. So this is the MongoDB query API. And what we can see here is we have the search operator, and it's kind of like JSON, right? It's very familiar, but you can think of each operator, you can think of it as like a stage. So we're going to create a bunch of stages. And within the stage, what we're going to do is we're going to get a data that comes into the stage. We're going to have the operator act on the data, then output the result. And the result can be outputted as a final result or goes into a next stage. So we have the search stage that uses the search operator to basically look for any documents that matches the query text specified on the path that we have. And you can see here that we're specifying the index we want to use. Remember, the index is the data structure that allows for location of data efficiently. And we're using the name text search index that we created an index with earlier. You have to make sure you get this part correct. So we have another stage called the limit stage. And this is a very simple stage because we're using something called the limit operator to basically say, yes, the search stage has given me a bunch of results, but I only want 5. And I only want 5 documents, I only want 5 results. And that's what that does. Then we have the project stage, which is going to project out of each document, these fields that were specified. You want to project out the embedding field. Now, why might you do this? The embedding, the data in the embedding field is actually a lot, and you don't need it. After you conducted your semantic search, your vector search operation, you don't need it for downstream processes per se. So I tend to just remove this. And this makes things a bit quicker in downstream processes. So here we generate this pipeline where we have the text search stage that does the text search with the user query. Then we reduce the number of documents that we want returned. Then we remove some attributes from the document. And then we pass this pipeline into the aggregate framework that is enabled in the PyMongo client, right? We have it within the collection.aggregate, and you pass in your pipeline, and it will execute each of this process and give you the result, which will be a list of documents that meet the user query. Let's see that in action. Okay, so here we have the query text. I've created a scenario here. So let's assume a patient visits a pharmacist. I feel like I spelled that wrong. But yeah, let's assume a patient visits a pharmacist and they have a cough. And we wanted to get some drug recommendation using our system. We're only going to use text search, right? So searching by text. Use only text data for this. So we're going to pass in the query here is going to be cough. And when the query here that comes in as cough, we're going to search for that. We're going to then use the text search with MongoDB. We're going to search for cough against in paths in our review, in the drug name and the condition attribute. So let's look at what that looks like. We go into the drug reviews, and what we want to actually happen is when we pass in the query cough into the collection, we want to look in the drug name, the condition, and the review and actually get any document where there's a match with the query cough. That's essentially what we're doing. So we go back into the code here and we can run this cell. Oh, wait, we didn't run the previous cell. So let's go in there. We run the previous cell, then we can run this cell, and that's done. We can turn the results into, the result is actually in this variable, get knowledge full text MDB. My variable naming gets bad as we go through the notebook because I run out of like wasted name variables. But here we convert it into a pandas frame and we can visualize the result. And this is what you can see, right? You can see that the only results that we're getting back are ones that meet the query text, which is, we can see this has cough in the condition. So this, we only want the documents that meet the condition cough. So this will be data that you pass to like your RAG pipeline, you supplement it with a user query and pass it to an LLM. And it is basically, you're only looking for conditions that match this particular query text. Okay, that's it. That's text search, right? That's when you have the acronym RAG, RAG, Retrieval-Augmented Generation, what we've just done is the retrieval part of RAG. We've just retrieved the document. So, and there are different ways you can retrieve the documents. We've just done one with text search. Now we're going to move on to see how we can do one with vector search. And vector search is the operation behind semantic search. There's a bunch of narrative on how vector search works, but here we can look at the function. It's almost similar, right? Semantic search with MongoDB, we have a user query, and we're actually going to use the user query on the collection to actually retrieve any documents that matches the user query. But what we're doing here is we're going to embed the user query first. So we're going to take that user query, pass it into the get embedding function, and get a numerical representation of the user query that we'll then use and pass that as a query vector to then conduct vector search. Remember, vector search, imagine a high dimensional space. We're going to put this query embedding, this user query into the space, and we're going to look for where it sits in this high dimensional space, and then look for any of the nodes of existing vectors within this high dimensional space that are close to this query vector. Because the closer they are, the more similar they are in context to the query vector. So what we're doing here is we're creating a bunch of stages like we did previously. We have the vector search stage that uses the vector search operator. We have the index name. So remember, we had this index name that we initialized earlier. And then we have the query vector that we generated here, the query embedding. We pass it into the query vector attribute. And this is the attributes we need for the vector search operation. We say that we want the number of candidates that should be considered within the traversal of the HNSW graph to be 100, but then we really want the top end results. So here what we're going to do is we're also going to add a filter to the actual vector search operation. So remember, we created a filter in our index, which means if we pass in the right filter, we can actually then reduce the scope of the vector search operation. And then we have this project stage as well. We already know what that does. Now we're just going to run this function, and that function is okay. We see the tick over here. And here we can see I've kind of switched up the query. So I have a call for what drug can I use is the user query. And what we're going to do is use this function. We pass in the user query text. I remember we generate an embedding for it. And then we can use the embedding to conduct vector search against the embeddings within our collection. So we can run this. And we're looking at things in the drug review collection. And if we go and look back into MongoDB, in the drug review collection, we have this embedding. So the user query comes in, we generate this 1024 dimension embedding from the user query. Then we say with the query vector, right? What embeddings are semantically similar to it, right? That's what the vector operation does. So we go over here and we've already ran this. And now we've gotten our results. We only want 10 documents returned. And now we can see what they look like. And you can see by searching only using the embeddings, we're actually getting results that match cough, the scenario against cough, right? Remember, when we actually generated the embedding for this, we actually only embedded the review, right? But you can see in the review, the semantics or cough is being captured in some latent space and in that high dimensional space. And our search operation, our vector search operation, can retrieve all the documents that correspond to cough in some sense that is verified. And we can verify this because even though we can't see the full text of this review, we know that the condition is basically around cough, right? You can look at the data in your MongoDB collection to see what this says fully. But one thing to notice here is we have a similarity score here. So this number is between 0 and 1. The closer it is to 1, the similar the query vector is semantically to the documents within that we conducted the vector search operation on. So 0.87 is pretty high, and we go all the way to 0.85. So they're pretty high results. But one thing you notice here is we didn't pass in anything for a search filter, right? So we said search filter none. So we're actually searching through the entire vector nodes, right? Within our documents. We're actually within the index, we're actually searching through all of it, right? That's not necessarily efficient. There's a better way to do things, and that would be to put a search filter, use the search filter. So in this case, imagine within a health case scenario, right? You know that your patient, your customers or patients are going to be searching based on conditions. So you can actually create a filter on that data point to make your retrieval operation a bit faster, right? So that's what we're going to do here. And we're going to say we want 10 results, right? And we're going to just pass in the search filter, and we're going to pass it in here. And we're using the search filter on the condition attribute because in our data, in our documents, we have this condition attribute, and we're saying we only want conditions that have cough in them. So we go back here, and what we can see is this, right? We have our results are going to be over here, and we can just visualize it. And you can see that we're only getting results that actually have the condition cough in them, even though we're not searching against the condition attribute. So, but because we're setting the filter to only give us results with cough in them, even though we want 10 results, there's only 5 in our data set that actually have the condition cough. So you see the point of having that pre-filtering step, right? There's pre-filtering and there's post-filtering. The main difference is in pre-filtering, you're literally reducing the vector search space operation to the ones that match the filter condition. In post-filter, before you conduct your vector search operation, in post-filtering, you're conducting your vector search operation, and then you're actually doing the filter on the returned results. There are benefits to doing both in some cases. So that's it, right? So we've seen how we can do the retrieval, the R part of RAG, and we've seen how we can do search as a retrieval mechanism, and we've seen how we can do vector search as a retrieval mechanism. Just to finish things off, we can see how we can use conduct hybrid search as a retrieval mechanism for the R part of RAG. And in this hybrid search, I've kept a bunch of narrative you can read, but we're going to have a balance between vector search and text search. We're going to have a balance between them. I will explain this in a bit. I also explain it in text here. Just like the other retrieval method, we're going to have a hybrid search with MongoDB, and we're going to pass in the user query. We're going to specify the collection. But here we're using 2 indexes, right? We're using the vector search index, and we're using the text search index. We're going to specify the weight we want to give to each of the retrieval mechanism. And the rest of it is pretty much the same. We specify the number of documents we want to return, and we specify the path for the text search and the path for the embedding, where the embedding is located. So it's almost a combination of everything from both of the previous searches that we've done. So because we're doing a vector search operation, we have to actually embed the user query. And the key thing is we're using the rank fusion operator. And what it does is it combines two search mechanisms, two or more, and actually uses an algorithm called reciprocal rank fusion to re-rank these results from each of the search operation. So basically we do the vector search operation and we do the search operation, and it uses reciprocal rank fusion to basically create a re-ranking of these two search methods combined on in the database. And we actually have this limit stage to limit the amount of results we want. And there you go. And we actually have the weightage. And remember, this is 0.5 because we want to have a balance between both the text and the vector search. If you want to lean more to semantic or search by meaning, you can make this maybe 0.7 and make this 0.3 because this has to be a number between 0 and 1. And we have the project stage as well. We know what that does. So that's hybrid search. It's made easy. It's very simple when you're using tools like MongoDB. And we're going to use a query. We're going to use a query, which is, I have a cough. What drug would be the best? I'm just zooming in again, just already quite into the video, but just zooming in again. I have a cough. What drug would be the best? And what we're going to do is we're going to pass that into this function we created. And we can see that here. And we pass in the weights. We pass in the text search path, review, condition, drug name. And yeah, that is what we have. And we're going to generate an embedding from the query text here. So just want to make sure we ran this cell. Yes, we did. Let's run this one. That's done. And the results are stored in this variable. Let's see our results. Okay, so you can see we have the results of the operation using hybrid search. Okay, so we've seen 3 different ways to do the retrieval part of RAG. Next, we're going to go into part 2, which is where we're going to actually build out the RAG pipeline, where we have the augmentation and the generation. And we're going to see what that looks like. For this, in step 1, you actually have to use the OpenAI Python library. So let's just pip install that. So we're in part 2 now. We're moving away from retrieval, right? We've covered retrieval aspects. We look at different ways to retrieve information from a database. Now we're moving into the RAG. So we're covering the augmentation and the generation aspect. So you're gonna need an API key, an OpenAI API key. Okay. Once you have your API key, you set in your environment variable. Now let's actually set up the LLM, and we're gonna be using GPT-4o here. For some reason, I say the latest version, but it's not. You use GPT-5 or wherever GPT version is out. This cell is just testing out the LLM to make sure everything's working. So we're gonna initialize an OpenAI client. So from the OpenAI library, we import the OpenAI class, which allows us to create an OpenAI client, and we can use a chat completion API to actually get our generation. Or you could also use the response API as well. That works as well, whichever one you guys want to use. So for the completion, we're actually going to use the create method, and we're going to pass in the model. We're going to be using GPT-4o. And here we're going to pass in a message. So the message here, the row here is going to be developer, the content. We're going to specify what we want our LLM to behave as. And then we're just going to simulate like a message saying, row from the user, the content here is hello, and we can see what that looks like, right? So this should have a completion aspect to it, and we can see what the completion is. We just said hello, and here it says back to us, hello, how can I assist you today? So it's working. That's just the LLM working. Now let's set up the RAG pipeline. So in a RAG pipeline, you have your retrieval aspect, which we've seen. We have the augmentation and the generation aspect, which is what we're going to see. We're going to define a function called custom RAG pipeline that's going to put together everything in one function, where we could just pass in a user query, then get the LLM output. Rather than go through this, I'm just going to show you in code. So we have this custom RAG pipeline function that takes in the user query, and the user query will conduct some form of retrieval based on the collection we pass in. And when we do that, we're able to actually then pass in the retrieved documents like we've seen before, and augment that, use that as the augmentation to the user prompt, and then we generate an output from an LLM that is grounded in the data we've provided it with. Let's see this in action. So we have this variable called retrieve docs, and that's going to be using the hybrid search. So this is the retrieval part of RAG. So we're going to pass in the user query, specify the collection, and then we're going to use our vector search index over here. And remember, this function has some defaults. So if you don't specify, it's just going to use the default variable arguments for the function. So this is the retrieval aspect. So when we run this, we're going to have some retrieved documents. And now we're going into the augmentation part of RAG, where we're going to format the context, right? We have, for every retrieved document, we're going to actually we're going to extract the review, the condition, and the drug name. And we're going to create this formatted context that has the review and the drug name, right? So it's as simple as that. The review, the condition, and the drug name as one text, as one string. And we're going to do that for every retrieved document. And we're just going to keep on concatenating each concatenated string to this variable formatted context. And now we're going to go into the prompt, the augmentation. We're going to create this simple prompt based on the following information. Answer the user question. We're passing the user query, which is a user question. And then we're passing the formatted context. And we then give some instruction that says, please provide comprehensive answer based on the information above, which is this formatted context. Obviously, you can make the prompt a bit better here, go into the world of prompt engineering. But here you can see we then actually go to the generation aspect of RAG, in where we're passing the prompt, which contains the augmented user query that's been augmented with retrieved documents. And now what we're able to do is get generated response from the LLM that responds to the user query. Let's get this function ready. So now we have a user query. The user query is very simple. I have a cough. Can you help me with some medication? And I have a data set with medication. So I have the drug review collection. And let's run this through our RAG pipeline. What we're expecting is like a text completion that is basically going to reference some of the documents within our database. So based on the information provided, several medications are mentioned for treating cough, but they have mixed reviews. So it's going to then use some of the medications that we have in our data set. It says this medicine is mentioned in 2 reviews. Now it has the number of reviews that it has, and it gives us the review. So you see where we're going with this, right? It's very intuitive, right? And this allows us to start building interactive chatbots that users can find very useful, that are backed by some knowledge base, some data that you have within maybe your problem domain or within your enterprise organization. So that's RAG. That's it, guys. You've done the RAG of RAG, Retrieval-Augmented Generation. Next, in part 3, we're looking at how we can make things a bit more agentic, right? How can we create agents that can actually use knowledge sources to respond to user query? And the reason why you might make things agentic is so you create this autonomous computation and entity that acts independently and can actually respond to user queries and utilize tools and connected tools to achieve a certain objective. RAG being one of the tools that an agent can use. An agent can connect to other tools, it can connect to the internet, it can connect to other data sources or even MCP servers. So in this case, we're going to be using the OpenAI Agents SDK, which it's an open source library for actually building agents using OpenAI's paradigm. So we're going to create in step 2 of what part are we on now? In step 2 of part 3, we're going to be creating a minimal agent, right? And a minimal agent is very simple. It's just an agent that has an instruction, and that's it. No tools, just an instruction. That's why I call it a minimal agent. And with the OpenAI SDK, different methods allows you to place your agent in an execution loop that allows it to basically iterate itself and iterate on itself until it achieves the objective that it needs to achieve. So we're going to be seeing this. So I'm using GPT-4. Here you can use any other model. And here you can see what we're doing. We have from the agents SDK, we're going to import the agent class and the runner. The agent class allows us to build an agent. The runner allows us to execute the agent in an execution loop. So here we have an agent, a simple minimal agent. It's called Virtual Primary Care Assistant, and we give it a name. We specify the model that we want to use as its brain, and we give it the instruction, and that's it. So I've given it like a clear instruction, and we can run it. It's just going to be acting as a virtual care assistant, and now we can actually take our agent and specify it as a starting agent within this agentic execution engine, the runner engine, and we're going to use it. We're going to use our agent as a starting agent and pass it the input, which would be like a user query, which is get me information on cough medication and the reviews, similar to what we did in the RAG pipeline. So we're going to run this. Now we're running our agent. Our agent is being executed in a loop until it gets the information that it needs to get that meets this specific user query. And we can look at the final result. And you can see the final result is when considering cough medication, it's important to understand the different types and the intended use. Cough suppressants, and this is just generic, right? There is no actual medication there's examples here, but this is not coming from our data set, right? This is actually coming from GPT-4o. It's coming from the parametric knowledge of GPT-4o. That's where this information is coming from. It's not coming from any data source that we're providing it, but we can change that. We can actually give our agent tools that allows it to retrieve information from a data source to then answer queries. That is the RAG aspect that we just went through. We're going to bring that into our agent. And the way we do that is very simple. We're going to use this method, this decorator, as a Python decorator called function tool. And function tool acts against another function called get medication reviews. And what get medication review does is it takes in a user query and returns a bunch of documents. And this sounds familiar because we're just going to use the hybrid search with MongoDB function that we created earlier on. We're just going to use that as a tool for our agent to utilize. And it's that simple, right? Now our agent can, at its discretion, use this tool when it wants. But how does the agent actually get an awareness of this tool? That's where this function tool Python decorator comes in. And this is coming from the OpenAI agent SDK. And we can see here that it basically creates a JSON schema of everything within this tool, including the description of the tool. So you actually need to keep a description of your function, and this will be passed into the context window of the LLM as tools that it has access to at inference time, right? So you have to, same with the get medication review, the name is important, the tool description is important as well. And what this does is it basically creates a JSON schema of this tool and passes it into the LLM. So let's run this. We're just going to initialize this function. And how we make our agent aware of this tool is in the agent, we go into the tool attribute, then we append to the tools this specific function. And that's it. Let's run that. Now this is our agent has access, awareness of this tool. And what we can do is, remember this runner, we can just run it and say the starting agent is a virtual primary care assistant. It's the same one we initialized earlier, but now it has a tool to retrieve information. And I'm just telling it to get me information on cough medication and the reviews. And that's the same thing we did earlier on with the minimal agent. But here we have an agent that has access to tools that can go into a knowledge source. We're going to see what the difference is. And we can see that the output is a bit familiar, right? Because here we have our agent responding using our knowledge source and not just the parametric memory, right? We're not relying on the parametric memory. The response from the agent is using the medications that we have for cough from our data set. We don't need the information in the parametric knowledge of GPT-4o, but we do need its reasoning capabilities, its text completion capabilities, right? And we're then using information from our data source to make sure we're getting relevant output that is more specific to our domain and it's not generic. So that's why we have the RAG pipeline, and we're using RAG as a tool for our agent. And we could verify here that a tool was used by looking at the raw response from the run results. And we can see that a tool call was made using the user query call. We see the ID of the tool call, and the name of the function was get medication reviews, and it was a function call. So we can see that it was utilized, and we can see that there's a model response, and the model response is this. So that is an agent that has an access to tools and has some form of knowledge base. Now what we can do is give the agent multiple tools, right? Now we can give the agent information on past conversation. Remember, we have two collection. Let's give the agent a reference of all of the past information that has occurred previously. And here we create a function called get past medical conversation. We put this Python decorator on top of it, and then we use the semantic search. Now we're not just doing hybrid search, right? Now what we want to do is do just vector search, right? So this tool is going to use vector search. The other tool use hybrid search. So here we have the user query. We're using that semantic search. We've gone over this, and this tool is basically to look up previous scenarios, and that could inform an agent response as well. So we're going to just run this. Excellent. Let's create a new agent now. We're going to create an upgraded virtual primary care assistant that has access to two tools. We're going to use the same name. We're going to give it an instruction, but in the instruction, we're going to give it an overview of the tools that it has and specify when to use it. So this is just a bit of prompt engineering. Let's run this. Okay, now that it's done, we're going to then make our agent aware of the tools. So we're going to append in the tools attribute the two tools that we just created. So for this new agent, so it's going to have access to the get past medical conversation and get medication reviews tools. And we can verify he has access to these tools by looking at this tool attribute. We can see this agent has access to get past medical conversation tool and get medication reviews tool. So let's run it. Let's ask a query, which is, I have a cough. Can you help me with some medication and get me some relevant past scenario and conversation related to cough? So let's see what it does. So now the agent is now executing on the query, is now going to use the two tools. One is going to get some medication, then it's going to use the other tool to get some relevant past conversation. Remember, we had two collections in our database. So let's see the final output. Okay, let's see this. So this is familiar because this is what it gave us before. So it gave us the medication and the review, but in addition, it then goes and gives us a past medical conversation about cough. And we can actually look at what it's talking about. Here are some examples of past doctor-patient interaction. It's using information from that conversation data set. So chronic cough is saying the patient had a persistent cough for a year despite consulting specialists. Then we have persistent viral syndrome. And so, yeah, this is all information that we can see that it's using from our knowledge source. And now we're getting to that healthcare agent that we wanted to create earlier for this use case. And I have a screenshot of the traces tool that is enabled on the OpenAI platform. So you can also see the fact that tools where you use this for like monitoring observability. I'm not going to go into the actual platform itself, but in case you're using this, you can trace the execution of your agent using this as well. Okay, in step 5, we can actually take things a bit further. You can actually create like a multi-agent system where you have an agent that can call on other agents, right? So let me explain. So here we have a medication agent. Remember, we have an agent. We're going to create a medication agent. This agent is only going to have access to one tool, and that's the get medication tool. That's why it's called the medication agent. Then we're going to create the conversation agent, which you'll be able to get past medical conversation. Now, these are two separate agents. So I'm basically isolating the scope of what I want each agent to do and the tools they have access to. Now I have an orchestrator agent. And this orchestrator agent will be able to, with an input query, utilize the right agent to answer the input query. And maybe at times it might use both agents. So here, where one thing that OpenAI agent SDK can allow us to do is actually use agents as tools, which is interesting. So in the tools parameter for an agent, we can actually pass in other agent as tools. So that's pretty cool. There's another agent that I create, which is the Synthesizer agent. So the response we get from all of the agent orchestration, we're just going to have an agent that can generate a synthesized response based on a certain format and tone that we're specifying in the prompt. So again, we've created at least maybe 4 agents at this point. So now we're just going to run it, right? We have a function called virtual care assistant, it takes in the user query, and with trace, this will allow us to actually see the execution of, we can actually see the execution log of the agent. What we're actually going to do is, first we're going to do is, we're going to run the orchestrator agent. We're going to run the orchestrator agent with the user query. Remember, the orchestrator agent has access to other agents that it can use as tools based on the user query. And based on the results, what we're going to do is extract the output, the message of this result. And when we extract that, we actually take that and use that as input. We take the orchestrator results as input into the synthesizer agent as well. So we run the synthesizer agent and we assign the result of this execution to the synthesizer result variable. But the starting agent has a synthesizer agent, and we're taking the orchestrator agent result as input for this execution. And here you can see that the final output of this function is going to come from the synthesizer results, which is from the synthesizer agent. I can't even say the word properly. So now we can actually run this. We're running this within an async.io loop. And here we're going to actually run a virtual care assistant, pass in the query. So here we go. We're going to actually have an input. And this is the input is, what health concern can I help you today? We're going to pass it into this function, run virtual primary care assistant. So this is actually going to run in a loop and we can interact with it. So what healthcare concern can I help you with today is the input. And now we're just going to run this. So here we can actually interact with it. So I'm just going to say, it's saying, what health concern can I help you with today? Can you get me some information and medication on cough? Okay, let's see the output. And here what we can see is this query is being passed into the orchestrator agent. Now the orchestrator agent is now trying to figure out, okay, what tool should I use? Should I use the medication tool or the conversation tool? And then once it's done, it passes its result to the synthesizer agent that will be able to respond in the way that we want it to respond. So here we can see the orchestration processing step, and is able to get some medical conversation, and it's got some common medication for cough. Remember, we remember this. And now the final medical response is going to come from the synthesizer agent. And this is what it looks like, right? So the final response is from the synthesizer agent, and it has a summary. It talks about cough. It talks about medication. It talks about the reviews. Then it talks about the doctor-patient conversation examples. And this can be helpful for like a doctor or a nurse whenever they just need to do things on the fly. And it's a bit of a disclaimer. Okay, so that is a multi-agent system in a sense. Okay, what happens next is we're going to go into part 4. And what we want to do is we want to store the actual conversation, right? We want to store the history of the interaction, the back and forth interaction. Because one thing is we have an agent. We don't want to build an agent that forgets. We want to be able to interact continuously and then maybe pick up an interaction if we've left from where we've left it off. And you need some form of conversational history memory to make this happen. And yet again, you can use MongoDB as not just the knowledge base store, but you can use it as a storage for conversational memory. And we're going to see that in action. So here we're going to do a couple things. We have our MongoDB client here. Don't know why I did this because we already have it, but we can create it if it doesn't exist. And we're going to create a chat history collection. And it's going to be called chat history. And this is a variable for the collection name. And remember, we're just going to create a collection over here if it doesn't exist. And that's what this does. So let's run this let's run the cell. And we've created a chat history collection within the database that we have for the virtual primary care assistant. And we could go into MongoDB and look at that. We can just quickly refresh over here. So we have only 2 collection, but if we refresh, and here we can see we have the chat history collection, but there's nothing inside of it yet, but we have 3 collection now, chat history. Going back to the code, what we have here is we've created our collection. Now we have a function where we can pass in not just a user query, but a thread ID, and a thread ID will represent a conversation. So here we have a thread ID. We're just going to generate an identifier essentially that we can use to identify each conversation, right? This is a unique identifier for each conversation. And that will be like the object ID for each conversation. But once we do that, once we have a thread ID, for each conversation that is occurring, we can actually start to store an object. We could store an object, which would be the thread ID, the role, which would be the user, and then we're storing the message, right? The user query, and then we store the timestamp, which is now that the information is being stored. Step 2, what we're now going to do is, after we've stored it, we're going to then retrieve previous conversations from that thread ID, because what we want to do is create a conversation context for our agent to have to be able to know what has been previously said or previous interaction that we've had between any other user. So we create this conversation context by locating any thread ID that matches the query thread ID over here. So in step 3, what we're gonna do is we have our conversation context, and we're gonna use this. The conversation context now contains previous conversation and the current conversation query, and we're gonna use this and pass this into the orchestrator agent. This is familiar, and now we're gonna execute the orchestration agent within this agent execution, and now we're gonna have the results. From the results, we pass it into the synthesizer agent. We get the result, and then we store the result of the synthesizer agent as another object in the chat history that we can now use as a final response coming from the assistant, but also we return the response from this function. There we go. And that's how we're storing conversation, but we can see this in action over here. We have this function called run chat session, and we can actually have an interactive chat session going on. So it's going to say, what health concerns can I help you with today? Can you get me medications for a chronic cough? So here we're starting a new conversation with this specific thread ID, right? We're going to do a couple interaction with back and forth. So this is basically, we've just manually done this ourselves. We've had to actually get the previous conversation and actually place it into context using custom code. I'm mentioning this because in part 5, we reduced the amount of code we have to write. So here we've got the result. I'm going to ask it's giving us a result. We already know what this looks like. Let's ask like a random question. Okay, what what time is it? No, that's not a good query. Whatever. I'm just going to ask what time is it, and let's see if it's able to answer like the time. It's not really a good query. So, hey, it looks like, yeah. So you're just going to answer it anyway. So information gathering. It sounds like you're asking for the time. I currently don't have access to real-time clock data. Please check the time on your device. Nice. Okay. It's not answering the time. Okay. Let's end the conversation here. Just use Q to end conversation or exit. But one thing we can do is now see what's inside of this chat history. Remember, we had 0 documents, but when we refresh it, we should see we're storing some information. Now we have 4 documents in here, and we can look at what that looks like. So first, we have the initial user prompts. Can you get me medication for chronic cough? And we have the response from the actual assistant. Then we also have me asking what time is it? A useless question. and it's also then the response is I'm unable to provide the current time. But one thing is whenever we're going through the iteration and we can kick things up again, remember we've killed the chat, but because this is stored, I'm going to ask it what was my first question. And my first question was, can you get me medication for a chronic cough? So you can see the thread ID is actually a constant, which is very interesting. So it's a constant here. That's not interesting. I don't even know why I said that was interesting, but we have a constant here of thread ID throughout. And what we can do is use that thread ID in this chat session. But one thing I'm going to do here is I'm going to actually put dynamically, I'm actually going to specify the session thread ID, right? When the session thread ID is none, it's going to create one itself. But let me actually just pass this in by essentially programmatically. So it's going to use this session thread ID and is now going to use the previous conversation as context. So let's run this and then let's run this. Did I should be passing this thread ID in the chat session, but it doesn't matter. So I'm going to ask it, what was my first question? And remember, my first question was, can you get medication for a chronic cough? But it should remember it because we're continuing the conversation with the thread ID that was specified. And the first question was, can you get me medication for a chronic cough? And that's how we have that conversational history, and we can have that continuation of conversation and interaction at different points in time. So that's done. I'm just going to press Q here. Now, there was a bit of boiler code that we had to write for this, right? But one thing that OpenAI SDK agent actually has is something called session memory. And we actually can create a custom implementation of session memory that the OpenAI SDK agent can actually utilize. Very quickly, this part 5 of this actually goes through the same process. But one thing I'm going to show you here is we're creating a custom session called MongoDB session. And the key thing is this custom session, and the documentation is here, it has to match the session protocol that OpenAI SDK framework expect. And that means it has to have certain methods: get items, add items, pop item, and clear session. It has to have all of this method defined to be able to actually pass in, to be able for you to pass in the custom session, which is this MongoDB session that's custom made as argument into the runner class, right? The run method in the runner class. Now we can pass in this custom session handler that we specified ourselves. What we're doing right here in this custom session handler, I'm just going to explain it. It's a simple class. And what this does is on initialization, we're going to make a connection to our MongoDB client, get a reference of our MongoDB database and collection. But we're going to have a method called get items, and get items will actually get conversation around, it's actually going to get conversation that matches a session ID. Remember, like what we're doing in part 4, and that's what that does. And it organizes this by timestamp. So we have it in some form of order, right? And here, this function just returns the documents we've extracted using this collection.find method on the collection object. That's what get item does. Add item, what it does is for every conversation, it's gonna store it into the appropriate, it's gonna create a document, store it into the collection, and allocate it the appropriate session ID that we're using at the time. Pop item is very simple. This allows us to remove conversations, and we can specify the number of conversations we want to remove from the record. Then clear session, this actually just deletes all the documents of all the session that matches the session ID. So that's it. It's very simple, very intuitive, and very easy to understand. And again, we're just going to create a very simple agent. This agent is a research. This is an assistant, and it has the instruction to research a topic and return the most relevant information, right? Just research whatever topic. We're going to run this. And now what we have is we're going to initialize, we're going to have an instance of that MongoDB session class. And now what we're going to do is we're going to have a session conversation 1 to 3. This is the session ID, or it could be like the thread ID. We're going to have our connection string. We're going to have our database name. We're going to store the session in collection name, right? There's going to be a new collection called sessions created. That's all good. Now that's done, all session interaction will be stored in this collection. Now we can actually get our research agent, and I'm going to tell it, hey, my name is Richmond. I am an AI engineer researching LLMs and agent memory, right? And I'm going to then pass in to the argument for sessions, the session manager, right? The session handler that we created. So let's run this. We're actually going to print out the results immediately as well. So we've printed out the result. We're running this. So it's going to answer the query, and it's going to remember us. Hi, my name is Richmond. And this might take a while because one thing it's doing is initializing MongoDB client, and is also storing the session as well, the information of the session. And we can see, hi, Richmond, it's great to meet another AI enthusiast. I can't even say the word properly, but yeah, especially one focused on LLMs and agent memory, which is great, because I am focused on agent memory. So it's just giving us a bit of information on some of this memory of agent memory concepts and architectures and all the good stuff around memory. Okay, so this is good. Let's see if this was stored in MongoDB. So we can go back to our virtual primary care database, and we have 3 collections, and one thing we should have now is 4 collections. And the 4th one is sessions, and you can see we have 2 documents here, and we can see what it is, and we can see we have the ID here. Hi, my name is Richmond. I am an AI engineer, and we can see the response from the assistant. The content is right over here, being stored, right? Great. And you can see we didn't have to write as much code, or more specifically, we didn't have to have code that where we're passing in the previous chat history context like we did in part 4 into every execution, right? This has been done for us using this session argument and the session class. Okay, let's do another turn, right? What is a paper that introduces the attention mechanism in LLMs? You can take a break and answer this question. So we know the paper was attention is all you need, and the LLM should know this. And you can see it has this answer, and that is going to get stored in the current session as well. Now, in the 3rd session, I'm going to ask who were the authors of the paper. Okay, interesting. So we have the 8 authors, and it's got the authors. That's great. I'm going to ask another question. What was the year of the publication? Even though it kind of said it here, and it's given us a link to the paper, which is great. Yeah, the year was 2017. Okay, now I want to remove all the conversation that we've had using that pop item. Remember, I just wanted to remove it. I wanted to forget the conversation we've had. Now the agent should forget any conversation that we've had on the paper. It should just forget the conversation that we've had on the paper. So I'm going to ask it, what paper have we been talking about? Now we should have some form of amnesia, right? It should just forget, right? So let's see, what paper have we been talking about? So over here is like, hi, Richmond, based on our conversation so far, you haven't referenced or mentioned any specific paper yet. So you can see it's forgotten because we popped the recently inserted information, but we specified the number that we wanted, which was 7. We wanted to pop 7 messages, and the last 7 saved messages. So over here, what we're actually going to do is, I'm actually going to do something here, which is it doesn't remember our conversation, right, about the paper because we've removed it. But let's see, do you still remember my name? It does, obviously, because it referenced me. Yes, name is Richmond. So it remembers at least the first conversation where I introduced myself. Now, let's clear all the session, delete everything from memory. We can refresh this collection. And what we can see here is it has no data. We've cleared it all out. And we're going to ask it, do you still remember my name? And voila, our agent has memory loss now. So it's, hey, I'm sorry, but I don't recall your name because I don't have memory of past interaction. And that, my friends, is session memory, right? Session-based memory. I showed you how you can implement it with custom code. I showed you how you can implement it using the way that OpenAI agent framework wants you to. And you've been on a journey, right? We've gone through this notebook, and it's actually a journey. We started off with understanding what RAG is, right? From the retrieval aspect, we looked at what vector search is, what text search is, what hybrid search is. Then we created a RAG pipeline, right? So we created a pipeline that used hybrid search. Then we made things agentic. We created an agent that can use RAG as a tool and then use multiple tools. Then we went into the world of multi-agent architecture where we had an agent that can call other agents and use those agents as tools. And we had a synthesizer agent. And then we saw two ways of how we can implement some form of conversational memory or session-based memory within our AI agents in part 4 and part 5. So you've done really well. You've made it all the way here. If you enjoy videos like this, which are relatively long, let me know and I can keep making videos like this and go deep dive and really take you from zero to hero on a particular subject. So thank you for sticking around, and thank you, and see you again in the next video.